We've actually done studies for it even up to decades ago, but it just comes down to whether or not the mission had extra propellant left over and whether there was an operational reason to switch from an East Coast launch to a West Coast. This is just the first time all of it came together.
What we're going to do is we're going to unload the spacecraft really carefully, and then we're going to drive it a couple of miles to the Astrotech facility where they have a clean room all set up for us. We've got about 2 months here. All we got to do is clean it up, test it out, put the fuel in the tanks, and bolt it on the rocket, and off we go to Mars.
InSight is NASA's next groundbreaking mission, literally designed to break ground on Mars. Using probes and seismometers, InSight will listen for Mars quakes and measure how much heat the planet's interior gives off. If we're going to truly understand how rocky planets like Mars and Earth were created, we need to look inside.
It's unlike other missions that we've done to Mars. We have a number of orbiters, a number of landers that we've successfully explored this amazing planet. But this actually is the first mission where we're really looking on the inside, the inner space of Mars.
Sending a science mission to the Red Planet is never easy. Landing a probe on the surface is even harder. To accomplish this, InSight will have to shed its many components in a matter of minutes, bit by bit, like peeling an orange, until only the lander is left.
So the crew stage itself is the critical component that actually gets us to Mars. There's an aeroshell that absorbs the heat as we re-enter the atmosphere. That aeroshell enables us to go through the atmosphere of Mars successfully without getting the inside, the lander itself, too hot. We deploy a parachute. That parachute does two things. It really ensures the stability of the aeroshell as it's starting to get closer to the surface. It also slows down the spacecraft further until finally we drop out of the combination back shell and parachute, and then we do a propulsive descent down to the surface.
We know water exists on Mars, and where there's water, there could be signs of life. But we must ensure any organisms we discover weren't simply stowaways from Earth. This is where the Planetary Protection Team comes into play.
Planetary protection is what we do to responsibly explore other planets and moons in our solar system. In order to do that, we need to make sure that we send a clean spacecraft there. We would hate to get to another planet or moon and think we discovered life, but it was actually something that we brought with us. So we collect our samples on InSight, any part of InSight that's going to land on the surface of Mars. We bring it back to our lab and we process it using a NASA procedure. If we run into a situation where we take a sample and it comes back as having a higher number of bacteria than what we want, then we make sure that the engineers go back and clean those surfaces with the whole idea that we don't want to cloud our ability to potentially find life on another planet or moon.
Lockheed Martin Space of Denver, Colorado, built InSight with an extremely efficient design, streamlining what needs to be done at the launch site. They shipped the spacecraft to Vandenberg with no assembly required. Simply check it out, fuel it, test it, encapsulate it, and it's ready for launch.
The processing for our spacecraft has been very smooth. A lot of the processing had to do with fueling the spacecraft, removing some removed before flight items. Everything else was pretty much already installed on the spacecraft in Denver, Colorado before it was shipped here. And that's called a ship and shoot, which means there's not too much to do except for to fuel the vehicle and do some last minute power on checkouts of the onboard computers and subsystems.
These preparations are crucial. Everything must be working perfectly before InSight leaves Earth. This effort is designed to ensure a safe arrival and landing following the 6-month trip from Earth to Mars. In the meantime, United Launch Alliance, or ULA, is busy at their launch pad, Slick 3, assembling the world's most successful rocket, the Atlas V.
Well, I mean, we're building a rocket. What's not exciting about that? And really excited to be able to launch the first planetary mission from the West Coast.
First, ULA stacks their Atlas V booster onto the launch platform. Atlas V is powered by the mighty RD-180 rocket engine. The RD-180 is a powerhouse, burning highly refined kerosene known as RP-1 and liquid oxygen for thrust. For When the booster's fuel is spent, the Centaur second stage kicks in and finishes the job. Centaur won't actually hit Mars. It will fly just past it. Final course corrections will be done by InSight itself to enter the Martian atmosphere and land on the surface. Once fueling and testing is complete, the team from United Launch Alliance will encapsulate InSight inside its payload fairing, the shell that keeps InSight clean and safe during its dangerous ascent through Earth's atmosphere.
We're at the phase of the mission where we're encapsulating with the launch vehicle, and the ULA team with their fairings now come in and they take the two halves of the fairings and they make a clamshell around the spacecraft to help protect it for the environments that we see during launch. And we do that because as we leave the Earth's atmosphere, the air and the molecules in the atmosphere would tear up our spacecraft otherwise, and the fairing is there to protect us.
With InSight encapsulated in its fairing, it's time to move payload out to Slick 3. But this California coastline comes with its own set of challenges. The surrounding marine layer can swallow up a launch pad, reducing visibility to under a couple hundred feet.
So right now, it's on the transport vehicle and it's ready to roll. And we'll be rolling out around 2 a.m. At that point, we'll have a convoy that drives very slowly from the payload processing facility out to the Slick 3 Atlas V facility. And once it arrives, we'll hoist the encapsulated spacecraft up to the top of the mobile service tower and place it on the launch vehicle.
This morning when it was sitting on the truck and they put the crane on it, they started lifting it up. That's the last time this spacecraft's ever going to feel the ground of Earth. I'm just kind of jumping out of my skin. This is so exciting. We're getting so close to launch, and it's been a long, long road for me. This has been a challenging program. I mean, we've had a lot of technical issues to overcome. We actually had to stand down back in 2015, but since then we've gotten it all together, and things have been going so smoothly the last year. We really feel really confident about this launch now. We got it on top of the rocket. We're going to blast it off in just a few days, and when it gets to Mars and lands, finally it will have solid ground under its feet again and get to work on probing the depths of Mars.
But InSight won't be traveling alone. Hitching a ride to the Red Planet are a pair of CubeSats, twin satellites called Marco A and Marco B.
So Marco is a dual payload riding as a secondary mission on its way to Mars.
So Marco is a pair of CubeSats, and CubeSats are really small spacecraft. They're essentially the size of a large cereal box, so about this big.
It's going to be relaying telemetry from the entry, descent, and landing of InSight back to Earth in near real time. After InSight is deployed on orbit and is heading to Mars, Centaur, which is behind me, ejects Marco A into orbit, and it'll slowly rotate itself so that Marco B ejects 180 degrees on the other side of the vehicle.
But Marco is a technology demonstration mission. It's actually one of the smallest spacecraft we've ever launched to interplanetary space. It's the first interplanetary CubeSat. So in of itself, it has all of these technology that we've never tested in deep space before. So if Marco works this time, one of the cool things that we could do is actually replicate that system and fly it with other missions in the future. And whether you're going to Mars or Venus or maybe even further away to an asteroid, and you could think of it as bring your own telecom relay.
So everything went well today with the lift of the spacecraft and mate onto the rocket. It started off very foggy and windy, and right now it's a beautiful day, just typical California weather. And now we're ready to go to Mars.
But just as twilight falls across the base, the fog returns, cloaking the coast with a bone-chilling mist that will last until daybreak.
As we get closer to T0 liftoff time, a number of activities have to happen. There's a mobile service tower around the Atlas V rocket, and the InSight spacecraft is on top of the rocket enclosed in the payload fairing. So we're going to back that mobile service tower away from the rocket to leave it exposed just beside the umbilical tower.
Stain engineer, proceed with MST roll to park position. Roger. MST bores will be closed in park position. Roger.
The final launch pad preparation is underway. Once the mobile service tower is rolled back, InSight and Atlas V are just hours away from T0. Basking in the searchlights of the West Coast facility, they are presented with the glamour of a Hollywood premiere, fitting treatment for such an historical mission.
So there's a lot of excitement within the NASA launch team about the InSight mission. First time we're going to launch from the California coast, going to Mars. And what is really exciting to the team is this is the culmination of a lot of work. The teams have been working on this mission for over 5 years, and today is the day that they will see all of their hard work rewarded.
Status check to proceed with terminal count. Atlas systems. Propulsion.
Go.
Hydraulics.
Go.
Pneumatics.
Go.
LO2.
Go.
Water.
Go.
Centaur systems. Propulsion. Go. Pneumatics. Go. LH2.
Go.
Facility.
Go.
Range coordinator.
Clear to proceed.
Launch director.
LC, you have permission to launch. Go Atlas. Go Centaur.
Go InSight. Proceeding with the count.
We're at T-minus 8, 7, 6, 5, 4, 3, 2, 0. And liftoff of the Atlas V, launching the first interplanetary mission from the West Coast, and NASA's InSight, the first outer space robotic explorer to study the interior of Mars.
Seconds after liftoff, the rocket punches through the marine layer, lighting the night sky for miles, visible all the way down to Los Angeles. An infrared camera showing the long tail of the exhaust plume captures some of the ascent, as well as an onboard ascent camera.
And we're nearing booster engine cutoff, or BECO.
Back to 4.6 Gs in preparation for BECO. Boost phase cooldown has completed. And we have BECO. Shutdown looks good. Stage separation. We have box and fuel pre-start. G&2 purge firing. The RCS is underway. We have ignition and full thrust. And we have indication of payload fairing jettison. Looks like a good step.
And the payload fairing that was encapsulating the InSight spacecraft has been jettisoned. The RL-10C engine, the second stage of the Centaur, continues to burn.
An hour and 28 minutes into the mission, the InSight spacecraft and the Marco twins are deployed from the Centaur upper stage, beginning the long voyage to Mars, where InSight will go to work shedding light on secrets hidden in the depths of the Red Planet.
Hey there, I'm NASA astronaut Ricky Arnold. Welcome aboard the International Space Station. Today we're going to talk about the Space Station Truss. The truss segment is just about 100 meters from side to side.
A truss is a segment or part of the whole integrated truss structure. The trusses are used to support the 16 solar array panels, which provide energy for us, and radiators which get rid of excess heat that builds up inside the space station. The design of the truss involves triangles and beams which can be seen on Earth in structures like bridges. Why triangles? Well, this is because of their unique geometric properties, their methods of transferring loads, and their spatial openness. Triangles are more rigid than rectangular shapes because they have fewer joints. The larger number of joints in a shape, the more prone that shape is to being impacted by shear forces.
What I'd like to talk a little bit about today is some of the forces that can act upon the truss. Well, the first force I want to talk about is compression force. And compression force is just like it sounds, two things coming together. So if we apply a compression force to the truss, what do you think is going to happen? Well, let me go ahead and do it. And you can see right here where the truss would bend. What do you think the opposite force of compression is? Yeah, it's going to be pulling apart. We call that a tension force. And a tension force is what's going to help maybe even rigidize the truss segment, but it also could potentially pull it apart. I'm not going to pull apart this tape measure because we probably need it later for some work we have to do. Now, if you look carefully, this next force I want to talk about is basically kind of like a twisting force, and we call it torsion. And even when I just let go of the tape measure, you can see it will actually start to happen a little bit. You can start to see, because the center of mass is actually right here, where most of the tape measure is located. And when I let it go, the tape measure itself starts to twist just a little bit. Finally, the fourth force that can act along a truss segment is that can occur at a single point where two opposing forces work on a single point along the truss, just like they can upon the Earth's surface. Think about some earthquakes. You can have a plate that is, or along a fault line, where part of one side of the fault line is moving upward or being forced upward, while the other side is moving downward. And that force in one point in opposite directions is called a shear force. And we can also have that happen on the truss segment. Something like this. One thing to think about, where do these forces come from? One force, even though we're up here largely out of the Earth's atmosphere, we do still have drag with the Earth's atmosphere, which can impart loads on or impart a force on the truss segment. Another, I already hinted at earlier, is crew working inside. We're up here, we're exercising, we're moving really heavy pieces of equipment around. So we have an amazing engineering team on the ground, and we have specific disciplines that their job is to monitor all the forces imparted upon the International Space Station. They keep track of all those various forces I talked about and where they could be coming from, the atmosphere, visiting vehicles, or even things that the crew are doing inside the space station, and to make sure that those forces aren't significant enough to cause any damage to this wonderful laboratory and living space we have up here in low Earth orbit. Thanks so much for joining me today. We'll see you next time. So long.
Attention! NASA television programming on Galaxy 13 is moving from transponder 11 to transponder 15. The transmission modulation format is now DVB-S2 8PSK. This move is in line with the Federal Communications Commission's initiative to free up C-band bandwidth on domestic satellites in support of future 5G terrestrial communications efforts. Transponder 11 and 15 are both active during this transition. Distribution of NASA TV programming on Transponder 11 will end on August 29, 2022. For more information, go to nasa.gov/NASA-TV.
You don't remember this miracle, but it happened to you. You were born into chaos. Those first days were a blur. But then, by the power of your mind, you resolved that chaos into a universe. A small universe at first, but a supreme act of learning. From then on, you became a learning machine, acquiring knowledge at a rate that you would never match again. I'm Jim Franciscus. No one of us has been untouched by our advances in space. And I don't mean only the spectaculars, impressive as they've been. Join me as we look into some of the space explorations that so excite us and have such promise for improving man's environment that we dare not ignore them. For it is in the quest for such knowledge that science is bringing us closer to an understanding of who and where we are. And like that baby in the crib, helps us resolve our world, our universe. We who make our way in more mundane pursuits enjoy the results, applaud the discoveries, and then take the benefits of science for granted. But seldom do we think about the discipline each scientist faces. What we believe to be true today will be adequate for most of us. Not, however, for the scientist. He is driven quite simply because he knows there is more to know. And this knowledge, when tested and proved, will, as it always has, be used to improve the quality of our lives. "400 years ago, the lords and ladies, their jesters, the knights, and the peasants believed the solar system looked like this. The Earth in the center, the sun out there, going around us. One of the men thinking about this was a Polish doctor, Nicholas Copernicus. He found an answer that his mind couldn't resist. The sun is really at the center. The Earth goes around the sun. But the establishment wasn't easily moved. It was easier for them to move Copernicus and his Earth with him. But then came Johann Kepler, a German. He believed Copernicus, but thought he'd satisfy the powers that be as long as the new universe moved in perfect circles. But then Kepler saw the truth. His mathematics insisted the circles needed stretching. The orbits were elliptical. From Italy came Galileo. Hitting upon Kepler's notes, he came up with a telescope. And he saw the stars, myriads where others before him had seen only thousands. And he saw that the planet Venus has phases, like the moon, which proved it must be orbiting the sun. And the moons of Jupiter? If a planet could have satellites, why not the sun? Finally, an Englishman, Isaac Newton, discovered why the Earth and the planets move about the sun. It is the gravitational pull of the sun which keeps them from flying off into space. Newton told them,
"The solar system is a great clockworks. If you understand the laws of nature, you can make or do most anything." Really?
The human race saw, became a great learning machine, and made progress never before possible. Sure, you can credit Newton for everything you've just seen. However, the practical results from what appear to be a purely scientific discovery are often unpredictable. A good example that looks contemporary despite its origin in the 1800s is Michael Faraday's statement defending his research before an English parliamentary group.
Gentlemen, I do not know what this electricity can be used for, but I predict that one day you will tax it.
Give a man knowledge, then step back and see what happens to him. It seems to free him. And that's what's put us in space today. Until recently, almost everything we knew about space was learned through this tiny window, the visible light window. All the rest of the secrets of the universe were hidden behind windows of invisible radiations, low-frequency radio waves, infrared, ultraviolet, and others. Signals from the universe, energy that would unlock so many secrets, were blocked out by our own atmosphere.
And a pretty good thing, too, since part of the radiation generated by this invisible energy is harmful to us. But as for seeing behind these windows, the Earth's atmosphere makes it impossible, even with the largest, most sensitive telescopes. There is one solution. Go higher and higher, taking our telescopes with us, beyond the atmosphere to outer space. Out here, what was invisible down below is still invisible to our eyes. But here we can measure it, and by measuring the radiation, infrared, ultraviolet, X-ray, gamma ray, cosmic ray, we can tell the distance of the stars, the energy they are pumping into space, how the atmosphere of other planets is different from our own, the temperature of gases in interstellar space, the strength of magnetic fields, the speed of particles in galaxies. The measurements become numbers, and the numbers are rained down on Earth. And out of the numbers grow pictures. The Earth and its sister planets, the ultraviolet sun, the X-ray sun, radio sounds from space, and the word that there are more than 100 billion stars out there besides the sun. And with each spacecraft, each measurement, we are bringing the universe into sharper and sharper focus, resolving it, seeing it grow brighter and ever clearer in our minds. In a universe of billions of stars, there are billions of mysteries. What is the origin, age, and evolution of the universe, the destiny of the stars and galaxies? We have reached a unique moment in history where man has developed the tools to take scientific measurements that may unlock some of these mysteries. Our satellites will help us crack the secrets of our solar system, unlock the doors in the universe, and enable us to learn more about our own planet Earth. With this knowledge, we may be able to improve life and avoid disaster. Without this knowledge, we may be able to do neither. In the few years we have jumped into space, our image of the Earth's environment has utterly changed. We have found, for example, that instead of simply being surrounded by a magnetic field that faded out endlessly in space, we are actually encased in a vast space suit, the magnetosphere. And that this magnetosphere ends at about 40,000 miles. Ends because there's a great wind out there. A wind, mind you, where there is no air, no molecules that you feel pushing against your face when you stand in a breeze. This airless jet stream is the solar wind, and to stand in it unprotected would be like holding radioactive material in your bare hands. You saw our astronauts on the moon unfurl a window shade of metal foil, which they later brought home with them. Man was catching, literally, bits and pieces of the sun, fallout from the sun's nuclear hell. And that is what the solar wind is, fallout from the thermonuclear reaction in the sun. We wanted that sample because we live in a cavity in that wind, and we want to know how it is affecting us when there is a storm on the sun, changing our weather and blacking out our international radio communications completely. And we'll want to know what effect that solar wind has on life. How dependent are we on that magnetosphere? If another planet didn't have this protection, could it still have life as we know it? Or something else we cannot even imagine? There may be only one way to know. Go to the other planets. The inner planets, Mercury, Venus, Earth, and Mars, are relatively small, solid bodies like the Earth. Investigating them is our immediate goal. In 1973, the Earth, Venus, and Mercury will be lined up so that we can try a new way to go further in space. We'll launch our Mariner to Venus and then use the gravity of that planet like a roller coaster to give more speed and fling it into space toward Mercury. The first time we have ever been able to explore that planet. Venus is a paradox. It rotates the wrong way, for example, the opposite of all the other planets. Or perhaps we are all out of step, except for our lady in space, Venus. Why? Well, we really don't know, but if we find out, it may tell us more about how the solar system was put in motion than all the other planets moving counterclockwise. Venus is the brightest planet, but No one has ever seen it. We have seen the thick reflecting clouds that hide it, but not the planet itself. These clouds heat the planet. Any water on the surface of Venus would immediately boil off into the heavy atmosphere, more like superheated steam than water. Why bother? To satisfy a scientist's curiosity? No. No, to know our own atmosphere better, we have to know all atmospheres. We have to ask, how did the Venus atmosphere get that way? Is it possible we are headed that way? Are we mass-producing enough pollution, enough smog, that might trigger the change, upset the balance, change the beneficial effects of our atmosphere? Only to mire ourselves in a malignant envelope that alters our climate drastically, that in the end might extinguish human life entirely. On the other hand, might it be possible for us to reverse conditions on Venus, perhaps with vegetation or chemicals, so that the oxygen locked in the carbon dioxide of the clouds is released, so that the planet cools, rain falls, and it becomes more like Earth? Is it possible that we might seed this bit of matter in space, so that some future generation from Earth can become pioneers in a distant new world? Why not? On Mercury, the nearest planet to the sun, there's probably no hope like that. If this planet ever had an atmosphere, it was blown into space long ago by the pressure of radiation from the sun. Here we may be seeing for the first time a completely desolate planet with no protection from the solar wind. Looking at Mercury, we can ask, is this the way the Earth would be without a magnetosphere or an atmosphere? Lashed by the full force of the solar wind without hope of life. And what about Mars? Well, this is the planet where we hope to find life, or which will help us understand the life process. In 1965, Mariner 4 got our first close-up photographs of Mars. 4 years later, Mariner 6 and 7 returned for a more detailed look. They sent back fascinating pictures of the rugged surface and the polar ice caps. When you watched this on TV, did you really feel that the spacecraft sending back the pictures was actually 60 million miles away? Can you imagine 60 million miles? The next step will be to orbit Mars. This unmanned flight is scheduled for March in 1971. Then we'll colonize it with machines. Our Mayflowers and our Pilgrim Fathers on Mars will be Viking, orbiters and landers. On the way down, the landers will measure the thin atmosphere. While overhead, the orbiters make related measurements. Then, for at least 90 days, our mechanical astronauts will take pictures, analyze the soil, sniff the strange air of Mars, feel for moisture. Thus, we will obtain information about Mars from the ground up to the limits of its atmosphere. Perhaps the greatest interest will be in the lander's search for signs of life. We're pretty certain now that there is no man-like life there, but we were not always men. We were once just cells. Before that, we were perhaps just molecules of protein. And we still want to know if there's that kind of life, or if sometime in the past, life did exist on Mars, and what could have happened to it. All of this will lead up to the ultimate exploration by man himself on Mars. The outer planets, on the other hand, are entirely different from the inner planets. On Jupiter, Saturn, Uranus, and Neptune, there may be no place to land, stand, or walk. They're all several times the size of Earth, but they may not have a solid surface to land on. About the fifth one, Pluto, we don't know enough to call it either solid or gaseous. Our spacecraft will leave the Earth for Jupiter in 1972. It will be a 400 million mile journey, and it will take almost 2 years. Jupiter is the largest of all planets, 11 times the diameter of Earth and over 300 times as massive, but a quarter of the density. We will want to know what causes the color changes in the bands of clouds. What causes the mysterious red spot that drifts around the planet? And we'll want to know if before the Earth became what it is, it was perhaps first like this, a mass of gas and dust and vapor, a condensing part of a nebula out of which the sun was also forming. The protoplanet caught by the mother star's gravity, turning eternally in orbit, condensing into stone, into rock, destined to develop life, and then perhaps to become, in the end, like Mercury, an airless rock baking in the sun. To go to the planets beyond Jupiter will be a journey, an odyssey of years. To do so, our spacecraft will have to have an operating life far surpassing any we have planned before. Moreover, these planets are so far away, we shall have to take advantage of special conditions to reach them. In the period 1976 to 1980, they will be in an unusual alignment that will enable us to go to all of them. And this alignment won't happen again for over 179 years. The last time the planets approached anything like this grouping was when Thomas Jefferson was President of the United States. And you'll remember it was he who sent Lewis and Clark to explore the West to resolve the image of our country. On our first grand tour, we'll launch a spacecraft toward Jupiter. Then, using the roller coaster maneuver we tried out on the Venus-Mercury flight, we'll send the spacecraft to Saturn, use the roller coaster again, and the spacecraft will go on to find Pluto. It will be a 7-year voyage. In the second grand tour, the spacecraft will go to Jupiter as before. Then Uranus, on to Neptune, nearly 3 billion miles from Earth. After nearly 8 years, this spacecraft, which will be sending back its rain of data, will then escape the solar system and become the first object created by man to adventure into the galactic space of the Milky Way. A message to 100 billion stars that we are here, somewhere in the universe. How can we use the knowledge we will gain of the solar system for the betterment of our life on Earth? Our spacecraft are already being used to observe the Earth, to count the Earth's resources, provide better communications, better navigation, and to study the Earth's atmosphere. We live in this atmosphere. We breathe atmosphere. We see atmosphere. The sky is blue only because the atmosphere scatters the sun's light. It is here that the interaction between the sun and its solar wind and Earth, between oceans and land, between the Earth and its own atmosphere is acted out. This is where the hurricanes, the typhoons, tornadoes, tidal waves move across the stage. It is in that thin layer that the very fabric of life is both nurtured and attacked by nature. Can we do something about weather? Has our study of other planetary atmospheres given us any clues to the weather here on Earth? We think so. And in the next few years, the world is going to see the largest, most widespread scientific experiments ever attempted. It will be known as the Global Atmospheric Research Program, GARP. This will be a cooperative effort of the scientific societies and academies of almost the entire world. Everything that we know, everything that we can learn, will eventually be drawn together to create a model, a mathematical description of the atmosphere. When this is done, and with continuing observations, we hope to have the ability to forecast the weather accurately up to 2 weeks in advance. Think of the vacations saved, the picnic sandwiches, the rain check you wished you never got, the hairdo that was so special and had to look just right. More important, perhaps, than all the things you've just seen, we may be able to tell food producers everywhere in the world how much moisture they can expect, when to plant, how big their harvest is going to be, and where to distribute the food, where it is apt to be most needed. Today, we look to spacecraft to help solve these problems. In ancient times, man looked to the stars, and isn't that how astronomy began in the first place? We live under the influence of a star, our sun. Yet for 2 centuries after the invention of the telescope, we almost ignored the sun. It was perhaps too close to be interesting. Today, our orbiting solar observatories are making up the lost time. Soon we plan to put a telescope into orbit around the Earth with its instruments pointed at the sun, and an astronaut to adjust it, recover the photographs from time to time. We will call this the Apollo telescope mount. The sun, as we now appreciate, is a most unique laboratory. By measurements and logic, we are deducing its life history, and the life history of countless other stars. We believe that it was once a much larger, far cooler ball of glowing red gas. Cooler because the nuclear reactions that make stars hot were just beginning. Its own gravity pulled it inward, decreasing its size, increasing its heat, moving it into the main sequence of a star's life. It became the yellow-orange sun that rises in the morning over the life it has nurtured. As it grows older, it will probably grow hotter, larger again. Then, a great flash of light in the sky, a nova, it may collapse, and past its old age as a cool white dwarf, its story all but ended, perhaps. But from what we learn on the sun, we can instruct our other satellites what to measure among the other stars. Our orbiting astronomical observatories turning their eyes to see what is invisible from Earth. Or our radio astronomy explorers, spinning out arms longer than the Empire State Building is tall, reaching out for radio waves that come from stars, the planets, the Earth itself. They will find mysteries, some that we shall solve, some that will lead to other mysteries. For example, the Crab Nebula. Until a century ago, astronomers with simple telescopes saw this as a blur, then resolved its image further with modern telescopes, and now see in greater detail by space observations. In its center is a small blue star, a faint hot star, one whose history we believe is all but ended. Yet, from that point of light comes energy at a rate 50,000 times greater than the sun's. It is a pulsar, and it pumps an unbelievable burst of energy into the heavens 30 times every second. What does it mean to us? Well, if we can measure it, describe it mathematically, understand its laws, then perhaps someday we might be able to duplicate this newly discovered energy source, as we did with the nuclear reaction astronomers found on the sun, and perhaps even tax it. Who will we meet as we travel in and out of the byways and boulevards of space billions and trillions of miles in length and breadth? Is there a chance that we will find planets where there are beings like us or unlike us, but perhaps alike in their deep curiosity about where they are, where they came from, and who shares the universe with them? Many of us think so, because even in our own galaxy, with its billions of stars, there should be millions of planets on which life could have evolved. For we are like the child in the crib, its eyes open, resolving its first mystery. Oh, there it is, the great adventure of the universe, which it took man more than 6,000 years simply to define. And at last we are ready to go there, ready for the next great leap in learning that the human race makes to meet the challenges of the moment.
The human exploration of space is still in its infancy. The Apollo missions were just the first step in our goal to have astronauts working on the surface of worlds beyond our own. And as NASA plans its return of humans to the moon and eventually onto Mars, a team of scientists have come together to test and build some of the tools our future explorers may use on these journeys. Based out of NASA's Goddard Space Flight Center in Greenbelt, Maryland, this group is called the Goddard Instrument Field Team, otherwise known as GIFT. The scientists in GIFT collect data on some of the most unique terrains on Earth, such as glaciers in Iceland, lava tubes in Hawaii, Mar craters in New Mexico, and the desert regions of Chile. The goal is to conduct field research in geologic settings that share similarities to locations on other planets, moons, and even asteroids. Scientists call these sites planetary analogs, as they help us learn how to interpret data from across the solar system, while also getting a better understanding of Earth. In these environments, GIFT researchers test both commercial and newly developed scientific equipment. These are portable devices that could be used by astronauts, or used aboard future rovers or other types of spacecraft. These field instruments are capable of multiple types of analysis, with some providing instantaneous feedback. The team uses devices that can observe and characterize the landscape around a user, as well as ones that analyze the chemical composition and physical properties of materials found at and below the surface. The team also works with instruments that measure aerosols in the atmosphere, magnetic fields, and solar radiation. No matter which field campaign they are on, the scientists in GIFT are selecting and using their instruments to answer high-priority science questions. And to more fully capture the essence of how humans would explore the surface of the Moon or Mars, GIFT members also simulate astronaut EVAs, or extravehicular activities, at the planetary analogs they study. Both former and current astronauts have accompanied GIFT on these simulations. Overall, the Goddard Instrument Field Team provides a unique resource to NASA and the external science community by combining the studies of planetary science, earth science, and hardware technology. All of the tests, experiments, and data collected provide a blueprint for the human exploration of other worlds. And that's a great gift for those taking the next giant leap.
It's all about the Earth and what we can learn about it from the International Space Station. Hi, I'm NASA astronaut Tracy Dyson. Welcome to Station Life.
Houston on 2 for velocity calculation, steps 4, 5, and 4, 6. We're moving on to step 5.
Go right now for
You
that
can copy,
activity.
thank you.
Okay, Tracy, we copy and good information, we'll pass it along.
Welcome back. This month on Station Life, we're going to highlight the International Space Station as a platform for studying the Earth and take a behind-the-scenes look at what it's like to live and work aboard the International Space Station. You know, they say a picture's worth 1,000 words. The first pictures taken by humans from space forever changed the way we view ourselves and our world. If you've ever flown on an airplane in the window seat, you know the natural desire to stare out the window. Well, aboard the International Space Station, one of our favorite things to do in our off time is to stare at the beauty of our home planet.
Take a moment every day to look out the window and appreciate where you are.
Literally watch the Earth go by. We're going around the Earth once every 90 minutes. So you see a sunrise and a sunset every hour and a half.
It's just so vast and so vibrant in color, and so much contrast between the black that it kind of overwhelms you at first.
Don't just look out the window during the day. Go for the times between day and night, and then night and day, and take some time to look out into the universe at nighttime, because that's when you can really see all the stars. And you can see that the stars are not only like in a planetarium where they're sort of in a 2D field, they're actually 3D, and some are farther than others.
But you could see the blues and the oranges and the reds and the whites and the yellows, and really see more color about the stars, which indicates more about where they are in their life cycle, what kind of things they're burning and doing. And you would think that you'd get tired of looking out the window, but you never do.
Like I said before, a picture's worth 1,000 words. But in the case of International Space Station imagery, a picture could also be worth 1,000 lives. An imaging system aboard the station called Environmental Research and Visualization System, ICERV, captured photographs of Earth from space for use in developing countries affected by natural disasters. This is yet another way the orbiting laboratory is serving humanity off the Earth for the Earth.
SERVIR is a joint NASA and USAID program where we're working with developing countries around the world and strengthening their ability to use satellites to address the many problems that they have, including floods, fires, harmful algal blooms, and other types of events that they have where they can use satellites to really make better decisions.
We're using space information to help decisions that affect people in the village where they live.
When there's a major disaster, governments around the world come together and they provide all of the satellite data basically that the world has to offer. But there's smaller disasters that occur in the countries that we work in that may not make the front page of the New York Times, but in that country it's a really big deal. We asked ourselves, could we make a difference if we had a dedicated imager for acquiring imagery quickly after natural disasters, and to be able to provide that imagery back to the countries that need them, that have real decisions that need to be made with a very quick turnaround. As NASA, we looked in our own backyard and started thinking, could we use the International Space Station? The International Space Station was really a fantastic asset to take advantage of because it passes over 90% of the Earth's populated area every 24 hours. We developed an imaging system and we called it ICERV, which basically is a camera and a telescope system that sits inside the International Space Station and can collect imagery when it passes over natural disasters or other events that we need to collect imagery.
Initially, we were planning to take few pictures per day.
So we contacted all the USAID missions around the world, and in total we had more than 2,000 requests coming, for people who need images from ICERV.
And we moved to like 1,000 images per day.
We provided ICERV imagery for many, many natural disasters, including floods and fires, for deforestation, for volcanic eruptions, for earthquakes. So it was really a fantastic example showing how imagery from the International Space Station could be used in these times of dire need.
And now we have a huge archives of images of areas around the world. So this is something that was not really there before.
ICERV is an example of, in essence, making the International Space Station even more international and connecting space to village to better understand and protect our home planet.
Imagine bread loaf-sized satellites zipping around the Earth each day, imaging the globe and providing updates on the environment. Thanks to the International Space Station, this constellation of satellite image gathering has been made a reality. With the mission of photographing the majority of the Earth every day, Planet Labs created small satellites, individually referred to as doves, to capture ground imagery for use in humanitarian, environmental, and commercial applications. With the 2005 NASA Authorization Act designating the U.S. segment of the station as a national laboratory, the space station drives growth of a robust commercial marketplace in space through endeavors like Planet Labs. The Earth imaging mission of Planet Labs' DOVE satellites takes another leap toward creating benefits on Earth, resulting from innovation in space.
What happens if you wake up in the morning and you understand the state of the world as it is right now?
What could that data enable? How could people make smarter decisions? How could, for example, a farmer get better yield on his or her crops? How could somebody help disaster response? How can we use satellites to help humanity? That in many ways was the underlying thesis of doing Planet Labs, was to get data into the hands of people that could enable us to make smarter responses to that.
Planet Labs set out with the mission to photograph the entire Earth every day. And they thought, how are we going to do this? They said, let's build our own satellite.
Commercial imaging satellites, they're very large. They are very expensive. We took a different approach.
By making them really small, we can launch lots of them, and by launching lots of them, we can cover this, to get to this mission of imaging the whole Earth every day.
If we can do that, then we can literally change the way that we see the world.
They called it the Dove. It's about the size of a loaf of bread.
Our doves are basically mainly a big camera with a telescope looking down to take pictures of the Earth. We initially developed the first Dove satellite in our garage, so we kept on iterating the Dove design, we made it better and better, and eventually we put our first one into space. We had no idea what the quality would be like.
I mean, we didn't know if it was going to work.
But we got an image down and it was so beautiful that we knew at that point we could make this technology work.
Wow, we can really do this, and we can achieve this mission, which is something that is really needed for us to understand global change.
So we had done a couple of demonstration satellites, but the next steps we wanted to do was to scale it up, to test the first fleets of satellites.
But what made that possible was actually access to space.
So here's the problem, that in order to take pictures of the entire Earth every day, you're going to need more than one or two satellites. You're going to need a whole lot of satellites, and you're going to need to be able to deploy them really fast. And really, there's only one obvious choice on how to deploy that, and that's the International Space Station.
There was no other platform in the world in order to get access to space of that fashion in that time period than the International Space Station.
NanoRacks is our key partner with NASA.
At NanoRacks, we understood Planet Labs' vision, and we knew that we could help. We worked together to figure out what was going to be the best way to get as many satellites as possible, and we basically developed a new platform. It goes out of the GIM airlock, it's picked up by a robotic arm, pointed out into space, and it fires these little satellites off of the space station.
They were able to secure 28 of our satellites to be launched from the International Space Station, and that was known as Flock 1, our first constellation.
This opened up the whole world to satellite developers, people that could put things into orbit fast.
We now deploy these on a regular basis from the International Space Station. And now today, we're able to operate the largest fleet of Earth imaging satellites in human history.
And none of that would have been possible without the International Space Station.
The International Space Station does enable young, small companies like ourselves to get going in space.
The ISS provides a lot of opportunities for commercial companies to test and find where the market in space is going to be.
And so what we're seeing today is a proliferation of new ideas and new concepts. It's almost like it's a renaissance of what's happening in space. Buckle up and strap down, because this is going to be a rocket for all of us in the global community to be part of.
I used to think when I was growing up in Florida, lots of thunderstorms in Florida, you know, that here's this storm over top of me, and it's just this individual little thing that just is about a storm over Florida. And in fact, now after looking at the Earth from space, I see that that little storm in Florida is connected to Africa and Europe and all across the planet. And one of the most impressive things to see is how the Earth presents itself as live when you're watching these storms at night just trickle across the whole surface of the planet like its own nervous system. And the emotions of the Earth, you know, seeing storms that are developing, and the way you know from having that experience on Earth how it's probably impacting the people and the places down there. It's like, oh, is it upset and mad today versus the sunshine over some other part of the planet? And really gets you looking at it in a different way, an appreciative and respectful way. When you're crossing the deserts in Africa, and the way the dunes form, and they almost look like little, birds have run across the sand. And then this contrast you'll get from kind of the pinks and oranges and whites to these dark grays and almost deep blues and of rocks and everything that are intersecting with it. And the Bahamas and the northern coast of Venezuela, which quite honestly is, I think, the most beautiful place on our planet. It is just incredible.
Well, so far we've learned about using the ISS as a platform for iServe, which captures imagery of the Earth to provide disaster assistance, and deploying small satellites called doves. We expect good things to come from both of these experiments and look forward to their robust potential. NASA has selected proposals for 2 new future instruments, Getty and EcoStress. These sensors on the ISS will give scientists new ways to observe how forests and ecosystems are affected by climate change. Our next piece is about a recently completed mission of an Earth-observing instrument on the ISS called HYCO. Its name stands for Hyperspectral Imager for the Coastal Ocean. Check it out.
Carroll Township's a very rural area in northern Ohio, right on Lake Erie. Lake Erie has always been very important to Carroll Township and its residents. We use it for drinking water, we treat it, and it's really our livelihood.
In Lake Erie, for what unknown reason, suddenly the toxin level spiked, and that got through the treatment system.
It was indicated to me that it is pretty dangerous.
Cyanotoxins can cause skin rashes,
Headaches,
nausea,
vomiting, stomach problems,
nervous system problems,
liver damage,
to death.
We sampled and we had about 2.5 times the limit from the World Health Organization. The second sample was approximately 3.5 times. Our plant wasn't set up to handle what was coming in from Lake Erie. One of my biggest worries was actually hurting someone or even worse. So we shut it off right away, shut everything off. We had a very close call that day. The last thing you want to do is produce an unsafe water and allow your people to drink it. What we need is a better way to track and predict these cyanobacteria entries from our source water so that we can make sure that this never happens again.
A lot of times we'll find out after the fact that there's a problem with cyanobacteria in the water because the blooms already occurred. We either get results of sick animals or sick people. We need a paradigm shift. We need to go from being constantly reactive to these blooms to having a capability that allows us to become proactive. And the U.S. Environmental Protection Agency has been very encouraging of allowing for some high-risk, high-reward projects. And that allowed us to think outside the box, way outside the box. We've been fortunate enough to make use of a sensor on the International Space Station called HYCO, which stands for the Hyperspectral Imager for the Coastal Ocean.
HYCO consists of 2 instruments. One is a camera, and the second instrument is a spectrophotometer, which actually gives us the spectrum of light leaving that water.
The camera on a cell phone, for example, contains about 3 bands of data in a red channel, a green channel, and a blue channel.
HICO gathers light from the red, orange, yellow, green, blue, indigo, and violet parts of the spectrum. So using this technology, we're able to now detect those water quality parameters such as water clarity, what the phytoplankton concentration is in your water, how much light is being absorbed in your water, as well as what's the distribution of cyanobacteria in those waters, and does that concentration pose a health hazard?
So what this means is instead of waiting for someone to report that there's a problem with cyanobacteria bloom, we can monitor these water bodies from space
and get information that we can rapidly get out to the water quality managers through a smartphone application that we've developed.
So the app allows you to drop a pinpoint, and that pin can be placed in an area where a drinking water treatment plant may have an intake, and see what the current water quality conditions were. Each user gets that information near real time, so they can make judgment calls on whether they have to respond or take action.
Having the HICO on the International Space Station has been the ideal test bed for our research.
This is an amazing partnership. The Naval Research Laboratory had HICO on NASA's International Space Station. As HICO acquired a scene, it was transferred to the Naval Research Laboratory, and then the Environmental Protection Agency was able to do the analysis and the validation to send this information out through a prototype mobile application. Yes, this technology will reduce costs and provide near real-time information, but the big goal here is protecting humans. And if we can reduce exposures both to humans and even animals, then we've achieved our goal.
Our International Space Station is an unprecedented research platform in space, allowing researchers and scientists to conduct experiments that can't be done anywhere else. Utilizing the ISS as a ready-built platform for studying the Earth is well underway. So far, we've learned about iServe, Planet Labs Dove satellites, and HICO. 2 more experiments, or payloads in NASA speak, are on schedule to get to the ISS later this year. There's SAGE 3 and Lightning Imaging Sensor. SAGE 3 will measure ozone and other gases in the upper atmosphere to help scientists assess the ozone layer and how it's recovering. And that Lightning Imaging Sensor will monitor global lightning for Earth science studies and support operational weather forecasting and warning. Looks like utilizing the ISS to further benefit all of humankind? It's right on track. Thanks for joining us on Station Life at our behind-the-scenes look at using the International Space Station as a platform for studying the Earth. And be sure to follow us on Facebook and Twitter for the latest research news. And don't forget to download our straight-up gangsta app on your mobile device. It's totally legit. Until next time, we're working off the Earth for the Earth.
And liftoff.
10 seconds.
I think what you get a sense of is just how awesome the universe is and how tiny each of us are in the grand scheme of the wonder that exists out there. Realizing that and realizing just how overwhelmingly huge the Earth is, how overwhelmingly the physics dominates what we're doing, and that we're living in this solar system, galaxy, universe, lets you know that this is someplace kind of special. To be a part of the mission that serves on station, to be part of the mission that goes exploring space into this vastness is simply, one, an honor, but two, almost mind-changing. Mind-changing because we have businesses, we have missions here, we're focused on accomplishing the near-term goal. You get up there and you see the overwhelming portion of the Earth, the vastness that you're exploring into, and you go, wow, there is just so many questions, so much for us to do, so much for us to be able to help our brothers and sisters with. We had a special opportunity on space station because of the window arrangements to be able to seriously get immersed in the imagery. Going to the windows to watch areas that were of great interest. Patagonia, for instance, is just a beautiful, rich environment of earth tones as well as the glaciers, the water. It is just picturesque to the point where you go, I need to go visit that place. You want to find things on the Earth because it is memorable but also insightful. For instance, you're going over a tan and you go, oh, you know what, I bet you I'm close to the pyramids. And so you go to the window to take a look at if you are close to the pyramids, and then take some shots that you can take home. There are areas of the world that have volcanoes and you just happen to catch in one photograph 2 or 3 active volcanoes. It's a nice experience to be able to look out the window and go, wow, we really are seeing the living Earth living, and being able to be a part of it from such a vantage point. We saw Hades troubles while we were up there. The Gulf oil spill from the horizon occurred while we were up there. A number of hurricanes or tropical cyclones occurred while we were up there. You know there's a ton of energy in there. You know it's heading towards populated areas. It's not beautiful at that point. It's utter respect. It's what I would categorize it. I got visited by 3 space shuttles. Several of the crew members never looked outside the cupola before. I would bring them one at a time to the cupola. Tell them to close their eyes, open up all the windows, the shutters on the windows, and then tell them to open up their eyes. And that instant, when you're overwhelmed with that vista, when your eyes see nothing but the beauty of the Earth, every single one of them, every single crew member that I brought in there for that exposure cried. It is heart-stopping. It is soul-pounding. It is breathtaking.
Attention! NASA television programming on Galaxy 13 is moving from transponder 11 to transponder 15. The transmission modulation format is now DVB-S2 8PSK. This move is in line with the Federal Communications Commission's initiative to free up C-band bandwidth on domestic satellites in support of future 5G terrestrial communications efforts. Transponder 11 and 15 are both active during this transition. Distribution of NASA TV programming on Transponder 11 will end on August 29, 2022. For more information, go to nasa.gov/NASA-TV.
You just watched the trailer to the inaugural season of NASA Explorer's Cryosphere. The 9-episode series first launched in October 2018, taking a hard look at the great lengths NASA goes to study a part of the Earth that's often called the canary in the coal mine, a serious indicator of present, past, and future climate change. The show was filmed right here at our studios at Goddard Space Flight Center, as well as on location in California, Alaska, Greenland, Iceland, Antarctica, and the Arctic. Our crew followed many of the people you're about to meet into the harsh elements to capture their stories and were rewarded with breathtaking icescapes. When you think of a NASA explorer, you might imagine an astronaut or even a scientist studying the outer reaches of deep space. In reality, while NASA is unlocking the mysteries of our solar system, it's also looking for answers on Earth, the only planet we know of so far with life. So sit back and enjoy this 9-part adventure story filled with awe, triumph, loss, and courage. Be sure to stick around afterward for even more exciting bonus material from the 2018 Cryosphere field season.
Here at the end of the Earth, it still feels like a place for raw exploration and adventure. It's vast in all directions and ground zero for some of the biggest questions we have about the climate. But when we decided to make a series about the frozen places on Earth, we knew there would be one hurdle we would need to jump over first.
What is the cryosphere? The what?
Ooh.
I have no idea.
While I'm aware of the cryosphere, I don't actually know what it is.
It has something to do with ice. All right, that's all I got.
How do you get people acquainted with the cryosphere when most of us don't even know what it is?
Hey, so here we are in Washington, D.C., standing on the roof of NASA headquarters. That's the Capitol building right behind me. And what headquarters does is kind of serve as the focal point to connect the dots.
That's Dr. Tom Wagner, NASA's cryospheric program scientist at headquarters. In short, Tom is responsible for making sure NASA knows what the current status of the cryosphere is.
The cryosphere is everything from the snow that falls by your house to the icy reaches of the Himalayas, to the big ice sheets of Antarctica all the way at the South Pole, and also the frozen ground of the Arctic, and even some of that frozen ground that's currently under the ocean.
If you had to break it down, you'd have a mix of sea ice, snow cover, permafrost, ice sheets, and glaciers.
Right now, our best predictions are that sea levels will rise anywhere from 1 to 3 feet within the next 100 years. 3 feet of sea level rise has the potential to displace about 100 million people, which is a lot of people that need to find new homes.
Our current reality places us at a near tipping point, and the cryosphere is playing a huge part in that delicate balance.
So one of the things people don't know about NASA is that we study the Earth, and we've been doing that since NASA's inception back in the 1950s. And we study the frozen part of the Earth in a variety of ways.
Missions like SNOW-X, Airborne Snow Observatory, Oceans Melting Greenland, Operation Icebridge, Arctic Boreal Vulnerability Experiment, and countless other labs and individual researchers stand at the forefront of monitoring the cryosphere. But this year was a particularly big year.
3, 2, 1, and liftoff of GRACE follow-on, continuing the legacy of the GRACE mission of tracking the movement of water across our planet.
2 state-of-the-art satellite missions are being launched in a single year as part of a major attempt to understand Earth's frozen places. Our scientists are answering hard questions, sharing stories from the field, and giving their best predictions for what we can expect of a warming world. We're taking you with us as we follow NASA explorers on their journey to the frozen ends of the Earth as they study our rapidly changing world from satellites, planes, and boots on the ground. What we think of snow depends a lot on where it falls. If you live in the eastern US, maybe it's fun. Or maybe it's just a pain.
But if you live in parts of the world where they depend on the water that's in the snow for a large fraction of their total water that they use for drinking, for agriculture, for industry, or for hydropower, the snow is a very important natural resource. For example, in the western part of the United States, 80 to 90% of their renewable water comes from snow.
Snow is one part of the cryosphere that many of us have actually encountered before, but it also plays a critical role in regulating the Earth's climate. Through decades of remote sensing, NASA has kept a close eye on the ebb and flow of snow cover.
We now have a 52-year record of snow cover in the Northern Hemisphere, and we can see changes in the extent of snow cover over the time period, particularly in the last few decades, where we can see that the snow cover has been retreating. It's been melting a lot earlier in the springtime.
The extent is relatively easy to do, and it has been done over the years. What's tricky is, though, how thick is that snow? And it's even trickier how much water is in that snow.
That tricky part is known as the snow-water equivalent, or how much water would actually be in a layer of snow if it melted. NASA and its partners have taken to the air to help solve this elusive mystery. First, there's the Airborne Snow Observatory, or ASO, a small plane outfitted with a couple of instruments, one of which measures snow depth using LiDAR. LiDAR measures distance using light from lasers. Since 2014, ASO has flown over basins in California and Colorado, taking before and after looks at snow depth. Scientists subtract the snow-free summer data from the snow-on winter data to get an idea of the snow depth. There's no single way to measure all types of snow across the globe, and so NASA's other airborne campaign, SNOWX, is testing different combinations of sensors. This winter, SNOWX will test a new instrument, the Snow-Water Equivalent Synthetic Aperture Radar and Radiometer, or SWISAR.
SWISAR consists of two main components, one of them being the radar and the second one being the radiometer.
So with the radar providing the depth of the snow and the radiometer providing the density of the snow, we could put those two things together and get the snow water equivalent. Here in the chamber, we're going to measure different radiation patterns at our different frequencies and do some full system testing in this chamber. This chamber kind of enables us to isolate various types of radiation and interference. And in about a month, we're going to take the instrument, mount it on a Twin Otter in the Grand Mesa in Colorado, and we're going to fly it over the Grand Mesa and take various different measurements. This is what we call our engineering flight.
Making sure the sensors are calibrated is key in order to face the challenges nature will throw at them.
Half of the area that gets covered by snow every winter contains trees and forest. And the trees make it difficult for the sensors to see the snow that's underneath the trees, so it makes it difficult for us to measure how much snow there is. After the snow's had a chance to sit on the ground for a while, it gets denser and denser and denser over time, and it changes, which is another reason why snow is very challenging to remotely sense. It doesn't stay the same. It's constantly changing. One of the things that we often do in the field is go dig what we call a snow pit. We literally dig a pit in the snow so we can see all the different layers. The layering is very important.
All this digging is part of ground truthing SNOWX, a way of matching up what the airborne instruments see and what is actually sitting on the surface. The ultimate goal of SNOWX is to figure out what the best combination of instruments would be for a future satellite mission in order to get a global picture of snow.
We need to know how much snow is in a snowpack, because if we have too much snow and the snow melts too fast, then you can get flooding. And if you don't have enough snow, or if the snow melts too early, that can lead to a longer wildfire season, a more intense drought, and we need to know these things for water resource planning.
I can't really name anyone that has so much integrity as she does to the things that she's accomplishing. It's pretty amazing. Having Claire as a role model, just a strong woman in science and just so smart and so kind. It's just a huge confidence booster. Is that, hey, I could do that too, you know? That's possible, that's successful, that's what I want to do.
I would characterize her as a pioneer in the field.
The amount and quality of the work she's put out is second to none.
I know people who have a lot of tenacity. I know people that have integrity, but it's rare that people have both together in that, you know, that combination that Claire does.
Every morning, Dr. Claire Parkinson gets up before sunrise and runs 2 miles to work. She hasn't missed a day in nearly 40 years. To know the evolution of sea ice and how we observe it from space is to know Claire. This year, she's celebrating 40 years at NASA.
When I arrived at Goddard, which was in July of 1978, it was an incredibly exciting period here. Satellites were pretty new, but a lot of data had been collected.
NASA scientists were inundated with information, and Claire was in a cohort looking at sea ice, trying to make sense of a jumble of very raw, very new data. It was around that time that Claire and her team, at the time led by Dr. Jay Zwally, created the principal sea ice record that we use today.
How does something like that record help you do your job?
Oh, that record is fundamental to understanding sea ice. So without it, we wouldn't know how rapidly it's changing.
You may not realize it, but Claire's work studying the changing extent of the ice caps deeply affected our understanding of climate change, and relatedly our understanding of how climate change affects life on Earth.
One of the clearest signals for climate change that resonates with people has been this shrinking of the polar ice cap in the summer that we're able to see because of Claire's work.
After we had a record that was about 15-20 years long, we started noticing that the extent of the ice in the Arctic was getting smaller over time.
Sea ice is formed on the surface of the ocean and therefore is made from seawater. The biggest concentration is in the Arctic, and it's also where the biggest loss in sea ice is occurring. Every year, NASA reports on the sea ice minimum and maximum extents. As expected, the data is concerning.
By now, not only has this trend toward lesser ice continued, but it's even accelerated, so that now the decreases are greater than what they had been.
These trends are deeply troubling. But one thing's for sure. Our awareness of shrinking sea ice extent due to climate change was propelled faster and further after Claire Parkinson arrived at NASA.
I mean, she takes her job seriously, and the health and welfare of those instruments in space, yeah, she's on it. You know, it's one of the things you don't worry about because Claire's in the loop on these things. It's going to be fine.
In science, we stand on the shoulders of giants. on the shoulders of those who explored before us. But then, some among us are giants.
Tuesday was cold, I almost froze my toes. Oh, what's it gonna be next week? Who knows? That's climate. Oh, that's the climate you got. You take a bunch of weather and you average it together and you're doing the climate rock.
At a glacial pace, it means something's happening so slowly you can barely tell it's happening at all. That used to describe the very incremental movement glaciers and ice sheets experienced each year. But now that's changing. We're tagging along with 3 NASA scientists to understand the different lengths they go to not only investigate ice sheets and glaciers, but also communicate their often complicated science to the public. First, let's get oriented. Ice sheets, in pink, pretty much occur in only 2 places, Antarctica and Greenland. Glaciers, in yellow, play a key role draining melt off the ice sheet. Glaciers are also found in the high mountains, but we'll get to those in another episode.
So we know that something's happening in Greenland right now that's unprecedented in the last several thousand years.
That's Dr. Josh Willis, oceanographer at the Jet Propulsion Laboratory. Josh and his team are tackling one of the major environmental challenges of the 21st century, trying to answer fundamental questions about how melting glaciers impact sea level rise.
With my mission, Oceans Melting Greenland, or OMG for short, we're trying to understand just how much of Greenland's melt is caused by the oceans.
Along with being one of NASA's top scientists working on the cryosphere, Josh is passionate about demystifying climate change in typically unconventional ways.
I think by reaching out to people with a little bit of humor, a little bit of fun, maybe a song, you really have the opportunity to help people understand and come to terms with what we're doing to our planet. Because it's definitely happening and it's definitely a big deal, and we need to start preparing for it.
Down at the opposite pole, Dr. Kelly Brunt is getting ready for a major expedition.
In December and January this coming year, I'll actually be in Antarctica down near the South Pole collecting ground-based GPS data.
This is actually Kelly's second expedition to the South Pole. The first occurred in December and January of last year. Both surveys are critical and will help validate data collected by NASA's airborne campaign, Operation Icebridge, and the recently launched satellite mission ISAT-2.
All 3 of these layers, that ground-based, that airborne, and the satellite, are all tied together. The ground-based helps validate both the satellite and the airborne helps give us more validation data for the satellites, but also a bigger story with respect to the depth of the ice sheet and what's going on underneath the surface.
While some scientists are taking measurements in the field, others are looking for answers in physics and lines of code.
For me, those projections that we are doing, they do have a very personal meaning.
Dr. Sophie Nowicki is an ice sheet modeler. That means she and her team have the important job of forecasting how ice will change in the future, which also predicts changes in sea level rise. It's a job she doesn't take lightly, especially since urban planning and infrastructure use her team's models to make decisions about the future and safety of their communities.
When we make those projections that are 100 years in the future, 100 years can seem so far away, like I don't have to worry about it, it's just too far. But actually they are not. It's really like the future that we are looking at that our children or grandchildren will see to experience.
Whether it's learning to communicate in new ways, traversing a swath of Antarctica in a massive piston bully, or taking responsibility for an impactful climate forecast, our NASA explorers are pushing the limits of discovery every day. But on a very human level, they're people with families and friends who have a stake in finding out why and how the planet is changing as rapidly as it is.
some places on the surface, you might have these steep cracks and giant fissures that you would have to be careful not to fall into. In other places, you might see towers of ice right next to places that were relatively smooth. You might see places that were dark. Ice there takes the form of rock. It's frozen solid until you dig down into that ocean. So you may see some things that look similar to Earth, but you may see some things that are very different.
That voice you just heard?
I am Morgan Cable, NASA scientist.
I love it.
That's Morgan. She's probably one of NASA's best spokespeople for exploring our solar system's icy moons.
Europa is a fascinating place. It has this liquid water ocean that's about 3 times the volume of all of Earth's oceans combined. That's a lot of water.
To understand what makes Earth so special, sometimes you need to back up and take in the big picture. Remember, the cryosphere is every place on Earth with frozen water. And water is one of the biggest indicators for life.
Every place, at least so far, that we have found life, we found water along with it.
And so far, Earth is the only planet we know of with life. Although Europa isn't the only icy moon in our solar system, NASA has identified it as one of those places with key astrobiological potential. Morgan is a collaborator on the Mapping Imaging Spectrometer for Europa, an instrument selected for NASA's next mission to Jupiter's icy moon Europa. But she's also more than just a scientist working in a laboratory. She's preparing future NASA missions for success on the surface of alien worlds. This year, Morgan and her colleagues were in the field studying how life colonizes in fresh lava.
Earth, it turns out, has a lot of excellent, what we call analog environments, places that are similar enough to some of these other worlds that we can conduct some tests and we can do some analyses here. Now, they're not perfect, of course. They're not going to be exactly like Europa, but we can still learn a lot by testing in these environments. Some of these places include Antarctica and the Arctic Circle, but there are other places too, Alaska, Greenland, even Iceland. Any place where you have a lot of ice, because guess what the surface of Europa is made of? A lot of ice.
Studying the cryosphere doesn't just have big implications for Earth. It also matters for the frozen worlds in our own cosmic backyard.
If we're able to find life or evidence of past life on a place like Europa, that tells us that not only can life happen in other places, but it's common enough that it happened at least twice in the same tiny solar system. That means that the universe is wide open in terms of how much life we might find, the types of life we might find. It would revolutionize how we see ourselves and the possibilities for contact in the universe. It would be amazing. Oh, it's so exciting.
My interest in glaciers comes from the sheer size of these things and how much they're able to change on human timescales. And so the amount of mass and energy being transferred by glaciers around the globe is tremendous. It's an absolutely fascinating thing to study from space.
Mountain glaciers are some of the most charismatic parts of the cryosphere. Some might cling to the edges of cliffs at higher elevations, then lay bare and flat in a broad plain, looking cracked and weathered like elephant skin, before tumbling thousands of feet toward the sea and terminating in a dramatic calving front. They're like motion frozen in time, until they aren't. They tell a story about the distant past and yet are incredibly responsive to the present. You can understand why they'd be captivating to all of us, and especially cryospheric scientists. Meet Alex Gardner, a cryospheric scientist at NASA's Jet Propulsion Laboratory, who is going to help break down what a classic West Coast North American glacier might look like, where high amounts of snow dump onto the mountains.
And at higher elevations, there's melt in summer, but not enough melt to get rid of all of that snow. And so that snow accumulates, it compacts, it turns into ice, and it starts to flow under its own weight, and it flows down the valleys. And as it flows down the valleys, it actually carves those valleys out and it makes them deeper. And so it creates these beautiful fjords where the ice flows down, snakes out and down to the ocean or to the lakes or further inland. And so that ice is flowing, it's moving.
Alex uses satellite data to study large-scale changes in glacial ice. But 2,000 miles to the north, Chris Larson from the University of Alaska Fairbanks spends a lot of time studying glaciers from the air. He's been flying over Alaskan mountain glaciers for many years, most recently on a NASA-funded mission called Operation Icebridge Alaska. He's absolutely enamored with his local rivers of ice.
And what do you love about mountain glaciers?
Well, they're in mountains, so they're really pretty.
You couldn't ask for a better way to experience Alaska on a large scale than to go flying around for campaign after campaign and look at all of the mountains in Alaska. Truly infinite. You just feel like you'll never see the end of them, and you don't want to either.
But Chris doesn't spend weeks away from home and family for the views. Chris and his colleagues at NASA want to answer some pretty big questions by learning more about Alaskan glaciers and how they tick.
You know, why does NASA care about these? Well, they actually disproportionately contribute a large amount to sea level rise.
In the long run, as the Earth warms due to climate change, the big ice sheets and mighty outlet glaciers of Greenland and Antarctica stand to contribute the most to sea level rise, simply because the vast majority of the planet's ice is stored there. But currently, it's the world's smaller mountain glaciers in comparatively warmer places, like Alaska and Patagonia, that are contributing about a third of all inputs to sea level rise, even though they account for only 1% of the world's ice.
It's mostly due to them being dynamic. They have water at the bed, which allows them to slide fast, and they react quickly to climate change and have higher velocities than their polar counterparts.
Back at JPL, Alex uses satellite measurements of global ice and computer models to predict ultimately how much sea level rise we might see due to climate change. But in the case of mountain glaciers, we also care about the local impacts of disappearing ice.
When we think of changes in ice sheets, we typically think of just what is the consequence for sea level rise and the future evolution of the ice sheets. But glaciers in other regions, like high mountain Asia, Alaska, the European Alps, these are places where changes in runoff matters to stream flows. In places like high mountain Asia, you have a lot of glaciers that feed the streams that flow down to populated regions. And that runoff becomes significant for water resources, irrigation, and agriculture.
Both Alex and Chris are passionate about understanding how glaciers are changing and what it means for our planet's future. They'll continue to use tools like elevation maps from the ICET-2 satellite and detailed airborne measurements to monitor changing ice.
What we're looking at is a legacy of the Ice Age. Permafrost and methane is a time machine. So what we're going to do is walk back in time. We're going to see old carbon, old bones, old environments, and none of those are in equilibrium with today's climate, so that's the problem. That world doesn't exist anymore, and it hasn't for 10,000 years. It was nicely and very delicately separated from this modern warmer climate by about this much moss. And when that moss goes away, whether for fire or for human disturbance or for warming, then all hell breaks loose.
permafrost. It's maybe the part of the cryosphere that's most out of sight and mind. It's fascinating how it formed in the first place and how it got loaded with so much carbon. In a minute, we'll go back underground with Matthew Sturm from the University of Alaska Fairbanks. But first, let's meet Peter Griffith, NASA's project manager for the Above campaign, which supports more than 70 science projects studying forest and tundra vegetation, wildfires, animals like birds, caribou, and Dall sheep, methane emissions from expanding northern lakes, and the impacts of climate change on people in Alaska, Canada, and around the world. Many of those projects have some direct connection to permafrost.
Permafrost is the hidden cryosphere. It's the permanently frozen soil that surrounds the Arctic, all across Alaska, northern Canada, and then across Eurasia. The ground has been frozen during the ice ages.
During the ice ages, there was not enough snowfall in the drier regions of Alaska and Canada to form glaciers there, so the land was suitable for vegetation.
What happened is that over thousands and thousands of years, all of that plant material got compacted and frozen every winter and buried and pushed down, so that today there's 300 feet deep of frozen water and dead plants and some pieces of dead animals too. Sometimes you find woolly mammoths in the permafrost. But most of it, of the organic matter as we call it in the permafrost, is frozen plant material.
Some of that plant material is now thawing and decaying, releasing its ancient carbon into the atmosphere, sometimes in the form of methane gas bubbling out of expanding northern lakes.
We started this field campaign because the Arctic is the part of the planet that is warming first and fastest. And there are consequences to this for permafrost. So during the Arctic Boreal Vulnerability Experiment, we're studying permafrost with people on the ground, from aircraft flying over the region, and also from satellites in space.
Another way to understand the permafrost is to take a walk below ground with Matthew Sturm and into the U.S. Army Corps of Engineers permafrost tunnel.
And they've dug this tunnel back into the side of a hill about 200 feet, and it goes sort of sloping down so that by the end of the tunnel you're about 100 feet underground, and you're surrounded by bones sticking out of the wall from the steppe bison and the mastodons that are frozen in it. There's sticks that are 40,000 years old, that you can touch with your hand. There's grass that's still green, that's tens of thousands of years old because it got frozen, right away, and it's never lost the green color.
But as fascinating as it is to see these relics of an ancient era, or to see a tree split in half by thawing soil, or even to light a ball of methane on fire from under winter ice, at the end of the day, Peter and his colleagues want to know just how much organic matter is frozen in that permafrost, and how fast it might be released.
Currently, we think that there is something on the order of 2 to 3 times as much carbon locked up as frozen organic matter in permafrost as there is carbon dioxide in the atmosphere. So releasing all of that organic carbon from permafrost into the atmosphere would be a real game changer. That would be a tremendous transformation of the planet's atmosphere. Now, the good news is that it would take a very, very long time for that to happen. However, we are warming the planet at a rate now that calls into question how quickly is that changing and what the consequences in the near future and in the far future are going to be.
We're at Vandenberg Air Force Base. We're about 20 minutes before the launch of ICESat-2. You might see the white light off in the distance. That's the Delta II rocket.
It kind of feels like an idea that was always going to just stay an idea. But no, it's real. It's sitting on top of the rocket.
And for me, it's kind of surreal. surreal. Like you say, it's been 10 years and it's hard to believe. It's like, we're really here? This is really about to happen? It's totally cool.
This is Dr. Tom Newman. Over the years, his work has taken him to some pretty remote areas to study changes in the ice regions of our planet. And his research, among many others, has defined the goals of the new NASA satellite, the Ice, Cloud, and Land Elevation Satellite 2, or ISAT-2.
And we have ignition and...
The story of ISAT-2 really begins with ISAT-1. ISAT told us all kinds of cool things about the ice sheet and about sea ice that we didn't really know to ask. That data allowed us to measure elevation change of ice sheets in a way that we hadn't been able to before, and showed that all the action on the ice sheets, the places that were really changing quickly, were around the edges. So when we were thinking about what could we do better next time, we knew that was one key component.
In addition to the edges of the ice sheets, ISAT-2 needed to measure a dimension of sea ice that remained elusive: its thickness. To figure out how thick sea ice is, you can measure the height of ice sticking out of the ocean, or freeboard, and compare it to the height of water between the sea ice flows, called leads.
The problem is, sea ice is really dynamic, and those cracks open and close various places in the ice pack throughout the day, throughout the year, and what we need to do is have measurements of the ocean whenever it's available, wherever it occurs in the sea ice pack.
To solve that problem, ISAT-2 was designed with a fast pulsing laser instrument to take precise, near-continuous measurements across its 3 pairs of beams. For 10 years, everything about the mission was designed to measure rapid changes in the most rapidly changing part of the cryosphere. But it has to get into space first.
But it's a huge transition going from the ground to in space. We've spent better part of 10 years, thousands of people have been involved, and actually seeing the rocket there on the pad with all of that work kind of all put together in one place, it's pretty amazing. And then getting up in the middle of the night to go watch the actual launch, it's sort of surreal in a way, because you've put so much time into it for so long, and actually seeing it over there is like, whoa, you know, it's a big deal.
3, 2, 1, 0. That's off. That's 1.
Thanks, sweetie. That was awesome. Totally cool. There it went. That was Atlas. Last Delta II, heading on up.
So Atlas has been turned on over the course of the first few weeks of the mission, really culminating for us with a laser. So this is our first look at sea ice data from ISAT-2, and it looks fantastic. The signal levels look great. We've got plenty of photons there. We're capturing ridges. We can clearly see the ocean. All sorts of cool stuff in there. And this is just our first data. It's only going to get better from here on out.
The data from ISAT-2 is well on its way into digging deeper into the unknown dimensions of sea ice sheets, and glaciers. It will shed light on changes in sea level and global weather patterns, and once again find new things about ice we didn't know to ask.
So my heart is definitely racing. I don't know about anyone else's. This is the stuff nerds dream of.
10 seconds. 9, 8, 7, 6, it's gonna 5, 4, 3, 2.
That countdown you just heard? We'll get back to that in a minute. Last episode, we saw the epic launch of ISAT-2, NASA's newest state-of-the-art ice-observing satellite. But now that that's in orbit, the pressure to deliver results is on.
Between launch and, the first ground returns, took 17, 18 days or something like this. It's a time when you're quite nervous.
9 years ago, Dr. Torsten Marcus took over as the lead project scientist for ISAT-2 during a time when the mission needed a champion.
You start fighting for a mission over, for 9 years now.
So when ISAT-2 was turned off for the first time 18 days after it was launched, only then would the science team know if the whole thing had worked. And it did.
First of all, it's kind of emotional, right? Being here, ISAT-2 was development for 9-10 years, and as a project scientist, you live a mission, right?
If it sounds like there's a lot of noise in the background, that's because Torsten is being interviewed from a plane 1,500 feet in the air. IceBridge was tasked with the job of bridging the data between the end of ISAT's mission and the beginning of ISAT-2, about a 9-year difference.
The goal is that it would run until ISAT-2 launched and then would have overlap with ISAT-2 as well, so we can get a really long, well-calibrated time series from IceBridge.
As the deputy project scientist for Operation IceBridge, Brick works closely with Torsten to make sure the two missions are syncing up.
The timing was everything during that mission, which was a real challenge, because not only do we need to...
Basically what you need to take away is getting an airplane and a satellite in space to fly over the same flight path at the same time and collect matching data is really, really hard. IceBridge was tasked with two objectives: check the accuracy of ISAT-2's data over land ice and over sea ice. They were able to lock in the land ice data fairly quickly in the mission, but the sea ice data...
It was really tricky. We waited day after day. Do we fly the sea ice? It's still on our list.
7, 6, it's gonna 5, 4, 3, 2, 1. Mark on the overpass 0435, 35 Zulu.
Here's what just happened. A plane 1,500 feet up and a satellite 308 miles up measured the